this video, we'll be looking at the second part of the further mechanics topic, simple harmonic motion. Now, simple harmonic motion is, in simple terms, a continuous back and forth motion, an oscillation about a central equilibrium point. The easiest examples to think of would be a pendulum swinging back and forth, or a metronome, as shown in the diagram. So this oscillation back and forth is always going to be experiencing a restorative force. The force acting on the object is always trying to pull it back to the central equilibrium position at the midpoint. So as it continues to move away from the center, it will be decelerating. So it's accelerating back towards where it came from. It'll eventually hit a stopping point and then change its direction, again demonstrating the acceleration in the direction of the center of the midpoint. So for there to be an acceleration, there must be a force. So we can easily see the displacement is proportional to the force experienced and the acceleration itself. So at the maxima, you will experience the most. Now, in the exam, you're expected to be able to sketch and recognize several graphs. Now, 3 of these, motion-based ones, are all linked together. But the energy one is much simpler. And it's in fact something you've basically done from GCSE level. So if we consider energy on the y-axis and displacement on the x-axis, we can show that the kinetic energy is at its maximum around the midpoint as it passes that central origin. And at each maxima, left and right, it will be at its lowest, where it reaches a stop. Now, potential energy will be the inverse of this. And that's easy to recognize because at any point, both kinetic and potential energies will add up to the same maximum, because energy cannot be created or destroyed, and this is always considered to be an isolated system. So there can be no more or less than that overall total. Now, moving from this, we need to look at the motion graphs. Now you can see that there are some grey lines dotted on each of these that are lined up. Each of those represent the same amount of space on each of these curves. Now, generally, the y-axis has a positive maximum and a negative maximum. So maximum displacement, speed, or acceleration, and the opposite for the other direction. And we're going to look how that changes with time. Now you can see here for displacement, it's not a perfect curve, I'm afraid, but you can see a nice and simple cosine function. Now this shows, starting from the maxima on one side, and the rotation back through the central point to the opposite maxima, swinging back and forth as we go. Now we need to be able to translate this into speed. So we know that at the maxima, at either end, left or right end, we have no speed. However, the speed is going to be at its maximum when the displacement is 0 at the central midpoint. Similarly, we can determine what the acceleration should look like. As we know, the acceleration will be at a maximum when the speed is 0, because that will be the point at which direction is changing, so the maximum change in speed. So these all link together and tell the same story, and you need to be able to translate one into another. Now, displacement and acceleration are very easy because they are simply inverted, flipped over. Speed is a little bit trickier to think through. It is out by 90 degrees, basically, pi by 2. But it's easier if you understand the graph and what it represents, that you can reproduce the story each stage of that oscillation. So there is one peculiar aspect for simple harmonic motion, and that is the fact that the amplitude doesn't really have an effect on the frequency or the time period. So it doesn't matter with a pendulum how high it's lifted, it will still complete its oscillation in the same amount of time. So it's a little bit of a weird quirk, not necessarily what you would assume to be true. But that does mean that time period and frequency are completely independent of the amplitude, and we in fact deal with them later. Now, acceleration is again something we need to fully understand. Again, going from these graphs, all three aspects of motion, displacement, velocity, and acceleration, are obviously going to come up as calculations. Now, for acceleration in particular, we have a relatively straightforward setup because it was representative of the force. And we know that that force acting on the object that's oscillating will always be trying to bring it back to the equilibrium position. So as a result, it must be a negative. So we have omega squared A as our equation, or omega squared X, I should say. Now, X is the displacement. And the reason I put A there originally is because that would be the maximum displacement, that would be the amplitude. And in fact, we have a second equation, which is the maximum acceleration, which is given by omega squared A. So these two are basically the same equation, where the maximum value obviously just takes it as a magnitude. The normal acceleration here is indicated as negative to show you it is always accelerating towards that central point. Whereas the maximum acceleration is at the point where the object will have stopped and is changing direction. So the negative has no real meaning at that point. So acceleration again is in meters per second squared. Angular speed, radians per second as usual. X is the displacement from that central position. So from the point of equilibrium, and is measured in meters as usual. And capital A is our amplitude, which is defined as the maximum displacement from the equilibrium position. Now, this idea of giving two equations, one for acceleration and one for the maximum acceleration, is again repeated later on with velocity. And it allows a bit of clarity, a bit of simplification based on the situation. So, moving on, we have our equations for displacement and velocity to consider. Now, if we consider displacement first, we know that it is a cosine pattern that we have represented it as. And technically, you don't have to start at that point, but it's the easier way to link to the equation. The equation being x equals a cos omega t. So x in this case is our displacement, again, from that origin, from that equilibrium position in meters. A is our maximum displacement, known as the amplitude, again in meters. And the cosine function is acting on the angular speed, omega, again measured in radians per second, and time, measured in seconds, which cancels out those units. Now, the time we're talking about here is the time at which we are actually looking at. So we want to know the displacement at time t. So it's not a time period, don't confuse it with that. It is the specific time that we are looking at this oscillation. Now, the velocity equation comes in two forms. Firstly, we get our standard velocity one, which is given as a plus or minus, depending on which vector direction we're dealing with as positive and which one's negative, as the oscillation obviously goes in both directions. And then we have omega root, and in that root we have a squared minus x squared. So this is slightly peculiar to look at, but not too hard to work with. We are simply looking at the change between maximum amplitude and the actual position it's at to know how much speed there will be. So v is our velocity, meters per second. It is vector, hence the plus or minus, and everything else is as we've stated already. But we also get an equation for v max, the maximum velocity that will be experienced. Now we know that the maximum velocity is going to be based on that amplitude. So we have an equation of omega a, because we don't have to care about the difference in its position in this case. So these are simply equations you need to be able to use and recognize from the graphs. Thank you for your time.